Welcome to Part D for Unit 3 for our course on statistics. And in the previous section, we were talking about doing a two samples design. We were talking about a situation where we had two groups, and we were looking for a difference between those two groups in their means. We were wanting to see if the mean for one group was different from the mean for the other group. We were doing a simple contrast. And in that section, I gave an example, a hypothetical example, where we had a sample of children, and some children were randomly assigned to a treatment where they were forced to wear costumes, and other children were randomly assigned to the control group where they received no costumes. And then we were looking for a difference between those two groups in their mean levels of happiness. And happiness was the outcome variable, variable y, in that study. And in that example, we talked about how we could calculate a descriptive statistic, and the descriptive statistic was simply the size of the difference between the two means. And we took the mean for the treatment group, group 1, that is y bar for group 1, the mean happiness for group 1, minus the mean for the control group, group 0, y bar for group 0. And the difference between those two means was -5 in our previous example. And so that meant that our treatment group was 5 points lower than the control group in their levels of happiness. And then we also calculated an inferential statistic. We calculated a t-value. That's the standardized error that we made in that particular study if the null hypothesis was true. And our t-value turned out to be -8.62, meaning if the null hypothesis was true, that study made more than 8 times the typical amount of error. And I talked about how we could determine the probability of that t-value, that is a probability assuming the null hypothesis was true. And I mentioned that in that study that a t-value of 8.62 would have a very small probability. It would be much less than 0.05. It would be much less than 5%. And so we would reject the null hypothesis and claim to have detected a non-zero effect in the study. Now, one thing that we have not done yet is that we've been looking at this descriptive statistic, but we haven't dealt with the fact that this descriptive statistic is hard to interpret. So in this example, it was an example where the treatment group was 5 points lower than the control group in their level of happiness. But how big of a difference is that? Is a 5-point difference a big difference? Or is that a small difference? How big of a difference is 5 points? And that's hard to tell because we're measuring these happiness units, which are just arbitrary units that don't have a meaningful value to them. So we need some way to decide how big of a difference this is. And this is an issue that we've already talked about. We've already talked about how we can deal with this problem. And we talked about how we can address this by calculating an effect size such as a D statistic. And that effect size will give the size of difference between these two groups in a way that is meaningful. It will use a standard scale that always has the same meaning so that results can be easily interpreted. And recall that a D statistic is where we take the size of difference between two groups, and we're going to measure the size of that difference in standard deviation units. And when we calculate a D statistic, we can easily interpret how big that is. We talked about how we can call a D statistic of 0.2 would be called small, 0.5 would be medium, and 0.8 is large. And so on the left, I'm just reviewing the formula for a D statistic. This is the same formula I showed you before when we talked about a D statistic. We take the size of difference between the two groups, y bar 1 minus y bar 0, and then simply divide that by our pooled standard deviation. And that will give us our D statistic, which is a meaningful way to report the effect size. It's the meaningful way to report our descriptive statistic. This value of -5, the difference between the two means in raw score units, that's hard to interpret. That's not very meaningful. But once we convert that into a D statistic, now we have something that's meaningful, something we can interpret. So let's go back to that hypothetical data set that we were looking at in the previous section and see how we would calculate a D statistic with this example. So on the screen, on the left-hand side, there's that hypothetical data set that we were looking at in the previous section, where we had a treatment group of children forced to wear costumes and a control group that did not wear costumes. And at the very top, these are the descriptive statistics that we already calculated in the previous section. And down at the bottom, this is the t-value that we already calculated. So how would we calculate a d-statistic with this example? So for the d-statistic, we're going to take the size of difference between our two means and divide it by the pooled standard deviation. And we saw that in this example, the difference between the two means, y bar for group 1 minus y bar for group 0, was -5. With this example, our treatment group was 5 points lower than the control group in their levels of happiness. So that we plug that in, that's the numerator for our d-statistic, and then we divide that difference between means by the pooled standard deviation. So how do we calculate our pooled standard deviation? Recall that in the previous section, we already talked about how to calculate a pooled variance and also how to calculate a pooled standard deviation. Recall that to calculate a pooled variance, we take the sum of squares for group 1 plus the sum of squares for group 2, and then we add those two sum of squares together and then divide it by the degrees of freedom for group 1 plus the degrees of freedom for group 2. And in the previous section, we calculated the pooled variance for this example, and we got a value of 0.667. And then to calculate the pooled standard deviation, we simply take the square root of our pooled variance. And so if we take the square root of 0.667, we get a pooled standard deviation of 0.82. Now, notably, in this example, we didn't actually need to go through all these steps of calculating a pooled standard deviation, because this particular example is something where I gave you a very unrealistic example where the standard deviation for group 1 was exactly the same value as the standard deviation for group 0. These two standard deviations are identical. Now, in real life, this would never happen. In real life, you would never conduct a study and get a standard deviation for one group that's exactly the same as the standard deviation for the other group. At least that would be incredibly rare to get that. But for this example, I've given you this hypothetical situation that's actually rather unrealistic, where the standard deviations for the two groups are identical to each other. So if the standard deviation for the two groups are identical, when we calculate a pooled standard deviation, we're going to get the exact same value. And you can see that all these standard deviations are 0.82. Notably, it can be useful to keep in mind the fact that a pooled standard deviation is essentially a type of average of the two standard deviations from your two groups. And so whenever you calculate a pooled standard deviation, it should always give you a value that's somewhere in between the standard deviations for your two separate groups. And if you ever calculate a pooled standard deviation and get a value that's not in between the values for your two individual group standard deviations, well, then you know you've done something wrong. You know you've miscalculated. So this can be a good way to check to make sure you've calculated your pooled standard deviation correctly, because it will always give you a value that's somewhere in between the standard deviations for your two individual groups. So now that we have our pooled standard deviation, we can plug that into our D formula and take the difference between two groups divided by our pooled standard deviation to get our D statistic. So in this example, our D statistic turns out to be negative 4.18. Now, notably, this negative sign is somewhat arbitrary because a D statistic of negative 4.18 is the exact same magnitude of effect as a D statistic of positive 4.18. The negative sign just has to do with which group you happen to put first and which group you happen to put second. If I reversed the order so that I called, say, my treatment group was called group 0 and the control group was called group 1, well, then that would reverse the sign of my D statistic and it would become positive. So whether it's positive or negative has nothing to do with the overall magnitude of effect. And in real life situations where I'm reporting D statistics, I often ignore the negative sign if it happens to be negative, because I know it's just arbitrary and it doesn't tell me anything about the magnitude of effect. So a negative D statistic or a positive D statistic, if they have the same value, they're the exact same magnitude of effect, regardless of whether it's positive or negative. Now, for this class, when you enter answers on the Canvas program, if you have a D statistic that's negative, you should keep the negative sign, because Canvas does not know that this is arbitrary, and you could get an answer marked wrong if you have a negative value and you list it as positive. So when you're entering answers on the Canvas program, keep the negative signs for your D statistics if you get them, because Canvas doesn't know they're arbitrary. But in real life situations, I often ignore the negative sign if I get one. So we have a D statistic of 4.18. So how big of a D statistic is that? How big of an effect is a D value of 4.18? Well, if you recall from before, we said a D statistic of 0.8 or higher is a large effect. So 4.18, that is a huge, in fact, that's a huge, unrealistically large effect. That's a gigantic effect. And once again, I've given you an example that's somewhat unrealistic. It would be unrealistic to do a study and get an effect size this big. But for this hypothetical example, that's what I've given you. So our D statistic is 4.18. In other words, there is a little more than 4 standard deviations of difference between these two groups. And that is an enormous difference. That would be an enormous effect size if we ever got a D statistic this large in a real study. Now, up to this point, we've been talking about how to calculate a D statistic for a 2 samples design. That is, we've been talking about how to calculate a D statistic when we have 2 groups and we're doing a simple contrast to see if there's a difference between those 2 groups. So how would we calculate a D statistic if we're doing a paired samples analysis? So recall that for a paired samples analysis, every case has 2 scores on the same X variable, and then we calculate a different score for every case, and then we calculate the mean of the different scores. So how would we calculate a D statistic in that situation? And essentially, we're going to do the same thing. Now, recall that with a paired samples analysis, we called our variable X, whereas when we were doing a 2 samples design where we had 2 groups, we called our outcome variable Y. But with a paired samples analysis, there's just one variable and we call it X. And so rather than having Y bar minus Y bar in the numerator, I've switched back to X bar minus X bar. And so I have the mean on X at time 1 minus the mean on X at time 2, so get a difference between those 2 means. And then I'll divide it by the pooled standard deviation. Now, with a paired samples analysis, there's actually a few different ways we could calculate a standard deviation, and there's some debate about the best way to do it. For this class, the thing that I'd like to do is the thing that makes the most sense to me, and also the thing that's the easiest to do, which is to simply do it the same way here as we did it for a 2 samples design. That is, we'll get the standard deviation for the X variable at time 1, and we'll get the standard deviation for the X variable at time 2, and we'll simply pool those 2 standard deviations, so our formula will be the same thing. A difference between 2 means divided by the pooled standard deviation. Now, at the very bottom here, I have a note that if you're doing a paired samples analysis, the number of observations for the first mean for X at time 1, the number of observations on the X variable at time 1 will be identical to the number of observations on that X variable at time 2, because we have a paired samples analysis and every case has 2 scores on the same X variable, so the number of scores on X at time 1 is identical to the number of scores on X at time 2. And in that situation, your pooled standard deviation will simplify to this formula down here. Now, if you want to, you could calculate a pooled standard deviation the same way as we did it for a 2 samples design. But if you want to take a shortcut, if you're doing a paired samples analysis, your pooled standard deviation will simplify to this formula. You simply take the variance for time 1 plus the variance at time 2. So you add your 2 variances together, divide by 2 to get an averaged variance, and then take the square root of that, and you will have a pooled standard deviation. So that's a shortcut you can use to get your pooled standard deviation whenever you're doing a paired samples analysis. So let's go back to that hypothetical data set that we were looking at in the section where we were talking about how to do a paired samples analysis and see how we would calculate a D statistic with this example. So recall that for this paired samples analysis, everybody has a score on X at time 1, and everybody has a score on X at time 2, and everybody has a different score. And we can calculate the mean of all the scores at time 1, the mean on X at time 1, and we can calculate the mean on X at time 2, and we can calculate the mean difference score. And it will always work out that the difference between the two means will be equal to the mean difference score. That is, X bar for time 1, 6.2, minus X bar for time 2, 4.2, equals the mean difference score. In this example, 6.2 minus 4.2 is 2, and the mean difference score is 2. And also we talked about how we could calculate 3 different standard deviations here. We could calculate the standard deviation of scores at time 1, we could calculate the standard deviation of scores at time 2, and we could calculate the standard deviation of the difference scores. Now, to calculate the D statistic, what we're going to do is we're going to take that mean difference score, or the difference between the two means, the mean at time 1 minus the mean at time 2, X bar 1 minus X bar 2, 6.2 minus 4.2, which is the same as the mean difference score, which is 2, and that will be our numerator. That's the difference between the two means. And then we'll divide that by our pooled standard deviation. So how do we calculate the pooled standard deviation? So we're going to take the standard deviation at time 1 and square it. And if we take our standard deviation and square it, what does it become? It becomes a variance. So we take our variance at time 1, we'll take our standard deviation at time 2 and square it, become a variance. And we'll plug that into our formula down here. So we take our variance at time 1 plus our variance at time 2, and then divide that by 2 to take the average of our variances the usual way. And then we just take the square root of that to get our pooled standard deviation. That's that shortcut formula I showed you on the previous slide. This is a shortcut formula we can use for a paired samples analysis to calculate a pooled standard deviation. Now notably, once again, I've given you an unrealistic situation in that the standard deviation of scores at time 1 is exactly the same as the standard deviation of scores at time 2. Again, in real life, that would almost never be true. You would almost never do a study and get the exact same standard deviation at time 1 as you get at time 2. And so because I've given you this unrealistic situation where the standard deviation is exactly the same at both time points, once again, when I pool those two standard deviations together, I get the exact same value. In real life settings, you would probably have slightly different standard deviations at time 1 and time 2. Now, one thing that could be a little bit confusing here is that recall that when we calculated the t-value, that for this paired samples analysis, everything was focused on these difference scores. And after we calculated the difference scores, we didn't need to know anything about the mean or the standard deviation at time 1 or time 2. We essentially forgot about all that stuff because we didn't need it. But notably, for this D statistic, I'm going back. I'm using this standard deviation at time 1 and the standard deviation at time 2 to get my pooled standard deviation across those two time points, and I'm not using that standard deviation of difference scores. This is actually the thing that there's some controversy about. Some people would say we should use that standard deviation of difference scores, but I don't think that makes as much sense, and it makes things more confusing if I have different ways we do it for each type of analysis. So it's simpler and I think more sensible to do it this way. So for calculating the D statistic, we're not going to use the standard deviation of difference scores, but instead we're going to pool the standard deviation for scores at time 1 with the standard deviation of scores at time 2. So in this example, we've got our difference between the two means was 2. Our pooled standard deviation was 2.6. 2 divided by 2.6 gives us 0.77 with some rounding. So our D statistic is 0.77. And if you recall, for effect sizes, a D statistic of 0.77 would be a medium effect. It's getting a little close to large. We said if a D is 0.8, that would be a large effect. So a D of 0.77 would fall in the range of a medium effect. So that is how we would calculate the d-statistic for a paired samples analysis. So we've been looking at how to calculate a d-statistic in different situations. And we looked at how to calculate a d-statistic for a two samples design. That was a situation where we had two groups and we were testing a simple contrast to see if there was a difference between those two groups. And then we looked at how to calculate a d-statistic for a paired samples analysis. That was a situation where every case had two scores on the same x variable, and we were calculating a mean difference score. And on the screen here at the upper left-hand corner, I have the formula for our d-statistic. Now, this is the version of the formula going back to the two samples design. This is the version we use when we have two different groups and when we're calling our outcome variable, variable y. And so we have the mean on variable y for group 1, and we subtract from that the mean on variable y for group 0, and get the difference between those two means and divide it by our pooled standard deviation to get our d-statistic, which tells us the size of difference between those two groups in standard deviation units. Now also on the screen below the d-statistic formula, I have that data set. This is that hypothetical data set that we've been using as the example for the two samples design where we have two groups. And if you recall, our situation here was where we had a sample of children, hypothetically, and some children were assigned to a treatment group where they were forced to wear costumes, and other children were randomly assigned to a control group and they did not wear costumes, and we were seeing if there was a difference between those two groups in their levels of happiness. So now recall when I very first talked about calculating effect sizes, I talked about two different basic types of effect size that we could calculate. We talked about calculating a d-statistic, and that's what we've been talking about here. And then the other effect size I talked about was the correlation. And I said that the d-statistic is something that makes the most sense in a situation where we have one dichotomous variable and one numerically scaled variable. And note that's exactly what we have here in our two samples study where we have two groups. We have one dichotomous variable, that's variable x. So variable x is our group membership variable, and it can take on only two values. It can be either a 1 if you're in the treatment group or a 0 if you're in the control group. So x is group membership, and it's a dichotomous variable. Y, that's our outcome variable, that's the child's level of happiness, and that's something that can range from high to low. So that's a numerically scaled variable. And so we have a situation here where we have one dichotomous variable, variable x, one numerically scaled variable, variable y, and so a d-statistic is the most sensible effect size we can report, and it makes sense because it tells us the size of difference between our two groups in standard deviation units. But now, for something fun, although the d-statistic is the effect size that makes the most sense, we could, if we wanted to, we could still calculate a correlation. And the correlation would also be a measure of effect size. We could simply calculate the correlation between x and y. We have our x variable and we have our y variable, and each person has scores on x and each person has scores on y. We could simply calculate the correlation between x and y. Recall how we calculate a correlation. We take a covariance, so we could calculate the covariance between x and y. I'll put COV to stand for covariance. And then recall that our formula for a correlation, we take our covariance and divide it by the standard deviation of our two variables. So standard deviation x times standard deviation y, and that would give us the correlation. I'll put R here, R, our correlation between x and y, covariance divided by the product of our two standard deviations. So we could calculate the correlation between x and y. And if we did that, that correlation would be an effect size. It's a value that would be a high value. Our correlation would be large if we have a big effect. That is, if there's a big difference between two groups, then the correlation will be a large value. If the difference between groups is small, then the correlation gets smaller. So as the difference between groups gets larger, the correlation gets larger. As the difference between groups gets smaller, the correlation gets smaller. If there's no difference between groups, the correlation will be 0. So the correlation is not as intuitive as the D statistic in trying to understand what it's doing, but it is a measure of effect size. And if we did calculate a correlation, in this situation, if we calculate a correlation, if we wanted to, we could give that correlation a special name. We could call it a point by serial correlation. And a point by serial correlation doesn't mean anything different than a regular correlation. It's just a fancy name that we can use in any situation where one of our variables is dichotomous. So if we calculate a correlation, and if one of our variables is dichotomous, if we want to, we can call it a point by serial correlation. It's just a special name we can give to any correlation when one variable is dichotomous. It doesn't mean very much. If we were calculating correlations by hand, there actually are some shortcuts we could use for hand calculation if we're calculating a point by serial correlation, but otherwise there's no difference and it really doesn't mean much. So point by serial is just a special name we give to a correlation where one variable is dichotomous. Now, if we wanted to calculate that correlation, there's actually two approaches we could take. One approach is the long way. We could go through all the steps of calculating a covariance and then taking our covariance divided by the product of two standard deviations to calculate our correlation. That would be using the usual correlation formula. But we don't have to do that. Another option is we could use this handy shortcut formula I have here on the screen here, where it says the square root of t squared divided by t squared plus degrees of freedom. And I have over here on the left, it says RPB. So R stands for correlation, PB stands for point by serial. So this is the point by serial correlation. And this formula that we're looking at here is actually a very useful formula. We're going to encounter the same formula at several points throughout this course, because this is a formula that we can use anytime we've done a t-test. If we've done a t-test for an analysis and we want to take our t-value and turn it into a correlation effect size, this formula will do that. And so if we're doing a study where we're looking at for a difference between two groups, that is, we're doing a two-sample design, and we're testing for a difference between two groups, and we're conducting a simple contrast, we could calculate a t-value for that contrast, and we talked about how we can calculate that t-test. We already talked about that. So once I have my t-value, if I plug that t-value into this formula, it will produce the correlation. And this will be the exact same value I would get if I were to calculate the correlation the long way. If I calculate the covariance divided by the product of two standard deviations, I'd get the exact same value that I get if I do a t-test and then plug my t-test value into this formula. And so this is a very handy formula we can use anytime I do a t-test and then I want to know what is the correlation effect size for this analysis. So let's see what a correlation effect size would look like for this hypothetical data set that we've been working with. So on the left, there's that data set again. And at the very top, I have those descriptive statistics that we calculated previously. And at the very bottom of this page, I have that t-test that we calculated previously for this example. And then in the blue box, I have the D statistic that we calculated just a little while ago. We got a D statistic of negative 4.18, meaning that there was a little more than 4 standard deviations of difference between these two groups, which was a gigantic, enormous type of effect size. And then above that, I have the calculation for our point by serial correlation. And we're using that shortcut formula where all we need to know is our value from our t-test and our degrees of freedom. And so our t-test, we got a value of negative 8.62. That was when we did our t-test to see if there's a difference between two groups. So I'll take that t-value, put it up here, and then I need to know my degrees of freedom. And this will be the same degrees of freedom that we used when we did the t-test. And recall that for a two-sample study, our degrees of freedom is equal to n minus 2. So our degrees of freedom is n minus 2. So we have a total of 8 children. And so our degrees of freedom are 6. So I'll just take this. We got our t-value of 8.62. I'll plug that there. And that same value goes right here. And our degrees of freedom is 6. So we have t squared, 8.62 squared, divided by t squared plus degrees of freedom, 6. And once I do that, then I take the square root of that, and that comes out to be, with rounding, 0.96. So that is our point by serial correlation. And note, that is also a huge correlation. Our D statistic is a huge effect size, and so our correlation is also going to be a huge effect size. It would be unrealistic to do an actual real-life study and get effect sizes this large, to get a correlation of 0.96 or a D statistic of 4.18. These are huge effect sizes. So note, we could calculate a D statistic or a correlation. The D statistic makes more sense, but a correlation is also an effect size. So this means we have two options for calculating an effect size anytime we're comparing two means. We could calculate a D statistic, or we could calculate a correlation. And both of these are measures of effect size. So that raises the question, which one should you use? Well, use the D statistic whenever you're comparing two means, because that's what makes the most sense. Recall that the D statistic makes the most sense when we have one dichotomous variable and one numerically scaled variable, and it gives us a size of difference between two groups in standard deviation units. So the D statistic makes the most sense when you're comparing two means. So I would say, whenever you're comparing two means, use the D statistic as your default effect size. And this would include both a situation where you're doing a two samples study and comparing two groups, and also if you're doing a paired sample study and calculating a different score. In both situations, you're essentially comparing two means, and so the D statistic would be your default effect size. And if you're comparing two means, you would only calculate a correlation as your effect size. At least in this class, you would only calculate a correlation if I specifically ask for it. So for this class, if we're comparing two means and I say, give me an effect size, then give me the D statistic, because that's the default. And only give me the correlation effect size in a situation where I specifically ask for it. One thing that could be a potential source of confusion that would be good to clarify is that just now I've been talking about this effect size correlation called a point by serial correlation. But if you recall, in a previous section for this unit, when we were talking about paired samples analysis, I talked about something called a paired samples correlation. And both a paired samples correlation and the point by serial correlation, these are both correlations, but these are correlations testing two completely different things. And so it would be good not to get these two types of correlations confused with each other. So the point by serial correlation, the one we've just been talking about, this is one of two alternate methods we can use to indicate effect size when we're looking at a difference between two means. So both the D statistic and the point by serial correlation, these are both effect sizes that are measuring the size of difference between the two means. So for example, if I have a treatment group and a control group, the larger the difference there is between my two groups, the larger my D statistic will be, and the larger my point by serial correlation will be. The smaller the difference between my two groups, the smaller the D statistic, and the smaller the point by serial correlation. They're both effect sizes. They're both measuring the same effect, which is the size of difference between two means. It's just that the D statistic makes more sense. It's easier to understand and interpret, and the point by serial correlation is a little bit harder to wrap our minds around exactly what it's doing, but they're both effect sizes measuring the same effect. In contrast, the paired samples correlation that we talked about a while ago, that's a completely different animal. This is something we can only do if we have a paired samples analysis. And recall, this is the correlation assessing the extent to which the rank order of cases is stable across two assessment points. So the person who scored the highest at time 1, does she score the highest at time 2? The person that scored the bottom at time 1, does she score at the bottom at time 2? To what degree is there stability in the rank order of cases from time 1 to time 2? And note that we can't even ask that question. If we were doing this two-sample study where we had two groups, we couldn't do a paired samples correlation because we don't have pairs. We don't have people with scores at time 1 and time 2, so there'd be no way to do a paired samples correlation if I have a two-group analysis. So the paired samples correlation, that's asking a question about the rank order stability of cases across two assessment points, and that's only a question we can address if we're doing a paired samples analysis, and that's a completely different question from whether or not there's a difference between means. And the question about the extent of difference between means, we have two options for effect sizes, a D statistic or the point biserial correlation. And if we're looking at a difference between means, again, the most sensible option is to report the D statistic. So in this unit, we've been looking at how to analyze data when we have two groups and we're making a contrast between those two groups to see if they differ from each other. And we looked at how we can calculate an effect size. So an effect size is a descriptive statistic that tells us about the magnitude of effect. And we saw that if we're making a contrast between two groups, the best effect size to report is a D statistic. The D statistic is the easiest effect size to interpret when we're making a contrast between two groups. And then we've also considered how we can calculate an inferential statistic in this situation. That is, the inferential statistic is the one we use when I want to take results from our sample and make an inference to the population. I want to make an inference about what I think the true population parameter is. And we saw how, for example, we can calculate a t-value. So a t-value is an inferential statistic, and then once we have that t-value, we could calculate a probability, the probability of getting the results in our sample, assuming the null hypothesis is true in the population. And then we could make a judgment about significance. We could call results significant or not significant depending on our probability. Now, whenever we calculate a t-value, and actually whenever we calculate any inferential statistic, inferential statistics always require us to make assumptions. That is, whenever we calculate an inferential statistic, we need to make assumptions about things that are true in our data set. And if these assumptions are true, we will get the correct value for inferential statistic. And if these assumptions are not true, then we will not get the correct result from our inferential statistic. For example, if I calculate a t-value and calculate the probability of that t-value, I will get the correct probability if my data set has met the required assumptions, and I will not get the correct probability if my data set has not met the required assumptions. So anytime we do an analysis and calculate an inferential statistic, it's important to be aware of the assumptions that need to be met for that inferential statistic to work. So what are the assumptions that need to be met for a t-test to work? What are the assumptions that we make when we do a t-test? So there are two assumptions that we need to make whenever we use a t-test to investigate a difference between two groups. And the first assumption is that in the population, the variances are equal. That is, the variances for the two groups are equal to each other. And because a variance is simply a squared standard deviation, we could also say it this way. We could say that in the population, the standard deviations for the two groups are equal to each other. That's an assumption we need to make. And if we violate that assumption, then our t-test won't be correct. And when we calculate our probability won't be correct. On the screen, I have a picture of a situation that would be a problem that would violate the assumption. I've got a picture of a control group, and the distribution of that control group has scores all clustered fairly close together. It's a fairly tight distribution where scores don't deviate very far from the mean. In contrast, I have a treatment group where scores are more spread out from each other. So the bottom distribution would have a larger standard deviation or a larger variance, and the top distribution for my control group would have a smaller standard deviation or a smaller variance. The control group scores are closer together. For the treatment group, scores are more spread out. This might happen, for example, say I did a treatment say I did my treatment where I forced children to wear costumes, and this treatment had a mixture of positive and negative reactions, that some children had a very positive reaction to wearing costumes and they got very, very happy. Other children, maybe they didn't care so much and they didn't change much at all. And then other children had a very negative reaction, and they got very upset by wearing costumes. So that might create a situation where scores in my treatment group just get spread out really far apart from each other. So my control group might have a small standard deviation with scores close together, and then in my treatment group, scores might be more spread out, and it might have a larger standard deviation. And if that happened, that would violate an important assumption of a t-test. And when this happens, when we violate this assumption, we call this problem heterogeneity of variance. So heterogeneity of variance is a situation where you have two groups, and in the population they have different variances. That is, they have different standard deviations. One group has a larger variance, that is a larger standard deviation, and another group has a smaller variance, that is a smaller standard deviation. And so we call that heterogeneity of variance. And when we have heterogeneity of variance, that means we have violated an assumption of a t-test. And if we were to calculate a t-value and then calculate its probability, our probability would not be correct. So to determine if we have a problem with heterogeneity of variance, one thing that people sometimes do is to calculate something called Levene's test for equality of variances. And this will be a kind of a significance test, except for it will be a funny significance test where we actually want the null hypothesis to be true. So in this situation, we're going to set up a null hypothesis that the population variances are equal. In other words, the standard deviations for the two groups are equal. That's our null hypothesis. The null hypothesis is that there's no differences between the groups in their standard deviations, that is, in their variances. And if that's true, it means there are no violations. If that's true, it means we have not violated that assumption that the population variances are equal. That means we do not have a problem with heterogeneity of variance. So we want this null hypothesis to be true. We want the variances in the two groups to be equal. So we can calculate this thing called Levene's test for equality of variance, and that will be a test statistic. It will actually come in the form of a t-test or an f-test. It can come either way. But once we have that test statistic, we can then determine the probability of that test statistic. And if the probability is less than 0.05, we call result significant and reject the null hypothesis. And if the p-value is not less than 0.05, then we say results are not significant. And again, this is the funny thing. We actually want the results to be non-significant, because if they're non-significant, it means we have not detected any violations. But if they are significant, that means we had a big enough sample to detect a problem with heterogeneity of variance. It means we have detected a violation. So in this case, non-significant means we have not detected any violations. Significant means we have detected violations. So we want results to be non-significant because that means we did not detect any violations. Now, notably, this process has a logical problem to it. And that problem is that, as I've said before, when we do significance testing, our results are based on sample size. If we have a big sample, that means results are more likely to be significant. When we do significance testing, we're answering the question, was our sample size big enough to detect an effect? And so when we get a significant result, it means our sample was big enough to detect an effect. And if it's not significant, it simply means our sample was not big enough to detect an effect if one existed. So this means if I have a very small sample, my results will probably be non-significant and I won't detect any violations. And if I have a very big sample, I very well may detect violations because this test is based on my sample size. And this doesn't seem like a very good way to determine whether or not you've violated the assumptions, whether or not you have problems with heterogeneity of variance. It's just telling you whether your sample was large enough to detect problems with heterogeneity of variance, but it really doesn't tell you whether you actually have a problem with heterogeneity of variance, or if you do, how bad that problem is. So this is an approach that has some problems with it, but you should be aware of this approach and know how to use it because it's one that people often use if they want to determine if they have a problem with heterogeneity variance. It's the common approach that's used, so you should be familiar with it, even though it's a rather problematic approach. So if you have a situation where you have a problem with heterogeneity of variance, that is, you have a situation where in the true population, the standard deviations for two groups are not equal to each other, that is, they have different variances. If you have this problem with heterogeneity of variance, there actually are some alternate formulas we can use to calculate a t-value that will fix the problem. There are some alternate formulas that will give us a correct t-value when we have heterogeneity of variance. Now, for this class, I'm not going to do very much with these alternate formulas. I'm not going to ask you to calculate them, and I'm not going to give you any examples where we have a clear problem with heterogeneity of variance and where we would need to use one of these alternate formulas. And part of the reason why I'm not going to do very much with these formulas in this class is the fact that, well, in real-life research situations, they're simply not used very much. In real-life research situations, I would say it's fairly common for researchers simply to ignore potential problems with heterogeneity of variance. Researchers often don't pay that much attention to this assumption that the variances for your two groups need to be equal. And part of the reason why they often don't pay that much attention to it is that this issue, well, to be honest, it isn't that important. Now, I'm sure there are some statisticians that would become very upset if they hear me say that, and they might start wanting to throw rotten fruit at me if I say this issue isn't very important. But oftentimes it doesn't make that much difference. So if I have a situation where I have heterogeneity of variance and I've violated the assumption, and if I were to calculate my t-value and then calculate the probability of my t-value, if I have a problem with heterogeneity of variance, my probability will be incorrect. I will not have the correct probability if I violated the assumption and if I have heterogeneity variance. But still, that probability is likely to be very close to the correct value. It will be incorrect, but usually not by that much. And so for that reason, I'm going to label this assumption as a less important assumption. It is an assumption of a t-test, and when we violate this assumption, we will have an incorrect value for our t-test and an incorrect probability, but oftentimes it won't be off by that much. It'll usually still be pretty close to the correct value, and so for that reason, I'm going to label this assumption as less important. Now, this is going to be very different from the next assumption I'm going to talk about. The next assumption I'm going to talk about will be a very important assumption. So what is that assumption? The second assumption we need to make when doing a t-test is an assumption called independence of observations. And this assumption is something that is very important. If we violate this assumption, it will make a huge difference in our results. So we need to be very careful not to violate the assumption of independence of observations. So what exactly is this assumption? So independence of observations simply means that each case in a sample is independent from all the other cases. It means that I don't have two cases that are related to each other, or that they influence each other, or that they are redundant with each other. Recall when I talked about the example of doing a paired samples analysis, I gave an example of a sample of couples, and in that example, I treated each couple as a separate case, and I did not count each partner within each couple as a separate case. In that example, it would be inappropriate to count each person as a separate case because within each couple, the people are related to each other. They influence each other. For example, if I was assessing relationship satisfaction in a sample of couples, within each couple, one partner's relationship satisfaction would be related to the other partner's relationship satisfaction, so I could not count that as two separate observations of relationship satisfaction. Or to give another example, say I was doing a study and my outcome variable was a measure of statistical knowledge, and I had a sample of students and I gave them a statistics test. But say in the sample, I had one person that copied all of her answers from her partner. In that situation, I could not count those two people as two independent observations because one person would have influenced the other person's answers. So those would not be independent observations. Now, maybe the most obvious example of a problem that would violate independence observations would be a situation like this. Say I was doing a study with a sample of Muppets. I have some Muppets down here, and say I wanted to see if there was a difference between, say, human Muppets and creature Muppets in how much they liked chickens, for example. And so I get my sample. I've got 6 Muppets here. So I do a study. I get a sample of 6 Muppets, and I give them a questionnaire measuring how much they like chickens to see if there's a difference between the human Muppets and the creature Muppets and how much they like chickens. But in my study, I say, well, I've only got a sample of 6 Muppets here. That's not a very big sample. I'd like to have a bigger sample, but it's really hard to recruit Muppets for my study. So what can I do? Well, maybe after I have this sample of 6 Muppets complete my questionnaire, I say, hey, how about everyone, let's do it a second time, and maybe I can double my sample. So say I do that. I get everyone to take my questionnaire a second time, and I say, look at that. Now I've got 12 Muppets. I got a sample of 12 Muppets. And then I say, wait a minute, before you go, why don't you complete my questionnaire a third time? And now I've got a sample of 18 Muppets. And hopefully you're saying, wait a minute, I can't get a sample of 6 Muppets and then assess each Muppet 3 times and call it a sample of 18. I can't do that. Why not? Well, the reason is, if I do that, I'm violating this assumption of independence of observations. For example, if I assess Gonzo here the first time, and then I assess him again a second time, and then I assess him again a third time, these are not independent observations. It's the same Muppet observed on multiple times. These scores are redundant with each other. So the problem here is that I'm violating that assumption of independent of observations. So that's a very important assumption, and we want to always be very careful that we never violate that assumption, because if we violate this assumption, then it will make a big difference in our results. Now, throughout this course, there will be many points where I will ask you a research question, and I will want you to be able to provide a statistical answer to that research question. And specifically, I will want you to be able to answer the question by providing what I call these 5 pieces of information. So for example, in our current unit, we're looking at research questions that involve a difference between 2 means. So how would we provide a statistical answer to that type of research question? In other words, what if our research question was this? Is there a difference between the means for these 2 groups? If that's our research question, what are the 5 pieces of information we need to provide to answer that question? So the first 2 pieces of information pertain to a descriptive statistic, and specifically a descriptive statistic that we're going to use to indicate the effect size. So what are we going to use to indicate the magnitude of effect to answer that question? And we simply need to provide the name of the descriptive statistic that we're going to use to indicate effect size, and then provide the value that we got for that statistic. And in our current unit, where we're looking at a difference between 2 means, recall that the best statistic to use to give an index of effect size will always be the D statistic. So if we're looking at a difference between 2 means, the name of the descriptive statistic that we'll use as an index of effect size will be the D statistic. And so we'd say the D statistic, that's the name of our statistic, and then we'll say what it's equal to. We'll say what value we got. So for example, maybe I did a study and got a D that was 0.82. That was a fairly large effect. And so that gives the name of my statistic, D statistic, and the value that I got for that statistic. And then next, we need to address that inferential question. That is, we need to do a significance test, and we need to provide what is the name of the statistic we're going to use for our significance test, and what is the value we get for that statistic. And in our current unit, when we've been looking at a difference between means, we've been using a t-test as our inferential statistic. And so the name of the statistic that we're going to use to address that inferential question, the name of the statistic that we're going to use to calculate a probability value and to do a significance test, we're going to calculate a t-value. So t will be the name of the inferential statistic that we're going to use. And so we report the name of our statistic and then the value. What is the value we got for our t-test? So maybe we did a t-test and got a value of, say, it was 2.45 or something like that. And then after we report the value we got for our inferential statistic, we need to report the probability of that statistic if the null hypothesis is true. And so maybe we look up the probability, and the probability of that t-value turns out to be, maybe it's 0.04. So also p is equal to 0.04. So that gives us the name of our inferential statistic, a t-test, the value we got for that t-value, and then the probability of our t-value. Now, one thing to note, if we're writing this out like in a paragraph, whenever I list a t-value, I'd always put the degrees of freedom in parentheses after I put t. So if I was writing this like in a sentence and reporting research results, I would put t, and then in the parentheses, I put my degrees of freedom would go in parentheses there, and then I put my value here. But if you're just answering answers on Canvas, maybe I ask you simply, what are the 5 pieces of information? And I just want you to enter them like on a Canvas question. You would not bother to enter the degrees of freedom. You would just give me the name, a t-statistic, the value you got for that t-value, and the probability. Note also that when you're entering answers on Canvas, there are several points where the instructions will say, enter the answer just exactly as it appears for the probability. And that's because sometimes I'll be answering this question and I'll use an output. We'll be looking at output from some kind of analysis, and there might be different probability values on that page, and I want you to know which one to use, which one is the correct one to use to answer the question. And they might be very similar values. One might be 0.008, one might be 0.007 or something like that. And so I want to know that you're looking at the exact right probability. And so a lot of times it will say, enter the probability just exactly as it appears. And whenever it says that, know that Canvas thinks it's a spelling item, and you need to enter it just exactly as it appears. Don't round, don't add any extra zeros, don't add any extra spaces. If the instructions say, enter it exactly as it appears, then enter it just exactly as it appears. So those are the 5 pieces of information you would provide to answer a question and to provide a statistical answer to a research question. You provide the name of your effect size and the value you got for your effect size. You provide the name of the inferential statistic you're doing to test significance and the value of that statistic, and then you would enter your probability value, your p-value. Now, in our current unit, when we're looking at a difference between means, our descriptive statistic will always be a d statistic, and the inferential statistic will always be a t-value. So that's pretty easy for our current unit. In future units, when we go on to look at other research questions, we're going to be looking at other statistics we will use to address these research questions. So in future units, our descriptive statistic will not always be a d, and our inferential statistic will not always be a t. But for right now, for this unit, if we're looking at a difference between two means, our descriptive statistic will always be a d, and our inferential will be a t-test. So, like I was just saying, if we're doing a contrast between two groups and investigating a difference between two means, our effect size will be a d statistic. The d statistic is the best effect size to use in the situation. It's the one that's easiest to interpret. And our inferential statistic will be a t-value. We will calculate a t-value and then use that for significance testing. We will use our t-value to make a judgment about whether we can reject the null hypothesis and call our results significant. Now, I want to take a moment to note that significance testing is the process that we're using to address that inferential question. That is, we're using significance testing to address that question about how well results from our sample apply to the entire population. And significance testing is a process that has both advantages and disadvantages, and it's not the only option we have to address that inferential question. There is another option. So let's consider what the advantages and disadvantages are of significance testing. One disadvantage is that it simply provides a dichotomous decision. It forces us to make this dichotomous yes-no decision. Either results are significant or they're not significant, and there's no in between. And a significance test does not provide any information about effect size. Recall that when we call results significant, it simply means we've concluded that our sample was big enough to detect a non-zero effect. We're simply claiming that in the entire population, the true effect is not zero. And we're not claiming anything more than that, and that's a fairly simple thing to claim. Maybe that's kind of a good low bar to have, to say we need to be able to at least reject that null hypothesis before we proceed to talk about effect size. But in and of itself, a significance test doesn't convey any useful information about effect size. So those are a couple big disadvantages. Now, a couple advantages. One is that it's the traditional approach that everyone uses to address that inferential question. It's widespread. It's the thing that everybody does, and you really can't understand research, and you really couldn't publish research today without doing significance testing. So it is the traditional approach that's used. And on one hand, significance testing kind of simplifies results by forcing results into this dichotomous yes-no format. Either it's significant or it's not significant, and that's kind of simplifying results, but sometimes simplified results are easier to remember. For example, if you're looking at a research study or a textbook and you have all these effect sizes and they all vary from large to medium to small and they're different sizes, it would be difficult to remember all these different effect sizes. But if we give results simply as, is it significant? Yes, no. Well, these 5 things were significant, these 2 things were not significant. Well, that simplifies results, and sometimes that makes things easier to remember. And sometimes in science, that's important, because if I have an important finding and I publish that, but no one understands what I'm talking about, well, that's not going to do any good. So in science, it is important to be able to find ways to report our results in ways that people understand and recall and remember what we are reporting. And sometimes significance testing might help simplify results in a way that make them easier to report and remember. But there is an alternative. We don't have to do significance testing. The other alternative to doing an inferential statistic is to do something called confidence intervals. So let's take a look at confidence intervals. We're not going to focus on confidence intervals that much in this class because they're not used as often as significance testing. But in many ways, if we wanted to have a debate about whether confidence intervals or significance testing is better, well, probably we'd come out saying confidence intervals are better. Confidence intervals have a lot of advantages to them because actually they do provide information about effect size. So let's take a look at confidence intervals. So, to talk about how to calculate a confidence interval, I first want to review how we determine the probability of t-values and then use that to lead us to a discussion of confidence intervals. So recall how we calculate a t-value. We take a statistic from a sample and we subtract from that the true population parameter, which we assume is 0, and then we divide it by the standard error of our statistic. And that always simplifies to a statistic divided by its standard error. And then we ask the question, what would happen if we do a study, get a sample of people, and calculate a t-value, and then we replicate our study, get a different sample, and calculate the t-value for that sample, and then we replicate our study and get a different sample and calculate the t-value, and we replicate our study over and over and over again an infinite number of times and get all the t-values from all of our replications. And so that would give us a distribution of sampling error of all these t-values. And that's the distribution that you're looking at on the screen here, this green bell-shaped curve. That curve is supposed to depict a distribution of sampling error from all the t-values we get if we replicate our study over and over again. And so if I were to do a study and calculate the t-value and say, for example, the t-value was equal to 2, well, that would mean if the null hypothesis were true, because we always assume the null hypothesis is true when we calculate a t-value. So if I get a t-value of 2, that means if the null hypothesis is true, well, then the statistic that I got from my sample is 2 standard errors higher than the true population parameter. And because this distribution is defined by a mathematical formula, and if I know the degrees of freedom, that is, if I know my sample size, if I know the degrees of freedom for my study, I know exactly what the shape of this distribution will be. So therefore, if I have my t-value and I have my degrees of freedom, I can determine the probability of that t-value if the null hypothesis is true. In other words, I can determine what is the probability of randomly selecting a sample with a statistic this high. Now, one thing to note, in this class, I'm always going to be focusing on something called a two-tailed probability. There's actually two options. We can look at a one-tailed probability or a two-tailed probability. A two-tailed probability looks at the probability of getting a t-value this extreme in either direction. So for example, if I get a t-value of 2, a two-tailed probability is what's the probability of getting a t-value that's higher than positive 2 or lower than negative 2 in either direction. So a two-tailed probability gives you the probability in either direction, the probability of getting a value this far away from the true population parameter in either direction, the probability of getting a t-value this extreme in either direction if the null hypothesis is true. In contrast, a one-tailed probability would only look in one direction. So if I was doing a one-tailed test and I got a t-value of 2, I would only ask about the probability of getting a t-value higher than positive 2, and I wouldn't ask about the probability of getting one lower than negative 2. So a one-tailed test only looks at the probability going in one direction. Now, a one-tailed test will have the effect of lowering the threshold for calling something significant. A one-tailed test is less stringent than a two-tailed test. Something that is not significant with two tails might become significant if you switch and do a one-tailed test. And for that reason, it's often viewed kind of like cheating. If you report one-tailed results in a research paper, it makes you look kind of suspicious. It makes it look like you're being lax in your standards. So for that reason, for this class, I'm never going to deal with a one-tailed test. We will always do two-tailed tests. So that's a review, again, of how we determine the probability of t-values when we do significance testing. So now, both if we're doing significance testing or if we're calculating confidence intervals, in both situations, we can talk about something called a critical value. And in significance testing, the critical value is the minimum t-value that's needed for a result to be significant. This is a value that we can look up on a t-table, and it will depend on the degrees of freedom in our sample. But if we know the degrees of freedom, we can look up the critical value. For example, if we had a very large sample, or maybe a sample nearing infinity in size, or degrees of freedom nearing infinity, if we had a very large sample and looked up the critical value for our large sample, we would find that the critical value is 1.96. And so that means that a t-value with this sample size, a t-value higher than 1.96 will be significant, and a t-value lower than 1.96 will be non-significant. Now, another way to think about this is that it means that 95% of the time, our studies will fall plus or minus 1.96 standard errors. 95% of the time, our t-values will be less extreme than 1.96, and 5% of the time, studies will have t-values that are more extreme than 1.96. That is, assuming the null hypothesis is true. Now, we can also determine critical values for other levels of probability. For example, if we have this huge sample and we were to go to a t-table, we could look up the critical value for a probability of p is less than 0.02. And if we look that up on a table, we would find a critical value of 2.33. That's what the table would give us if we had a huge sample size. And so what that means is that 98% of the time, t-values will fall plus or minus 2.33 standard errors from the true population parameter, and 2% of the time they will be more extreme. In other words, 2% of studies will produce t-values more extreme than 2.33, and 98% of studies will produce t-values that are less extreme. So that's how we can understand critical values for a t-test. Now let's move to a discussion of how to calculate a confidence interval. So when I calculate a confidence interval, I want to make a statement that I am 95% confident that the true population parameter falls within a certain range of values. In other words, I want to know, or I want to determine a range of values that I am 95% confident will capture the true population parameter. And that would be a 95% confidence interval. Now, notably, we could create confidence intervals for different levels of certainty. For example, maybe I wanted to know the range of values that I was only 80% certain would capture the true population parameter, and that would be an 80% confidence interval. Or maybe I wanted to know the range of values that I was 99% certain would capture the true population parameter, and that would be a 99% confidence interval. Now, the most common confidence interval used in research is the 95% confidence interval, so that's what we're going to focus on in this class. So, to calculate a confidence interval, first, we're no longer going to assume that the null hypothesis is true. We have this distribution of sampling error here on the screen, but I'm going to assume I don't know what this true population parameter is. When we did significance testing, we assumed that that true parameter is 0, but now I'm going to say I don't know what this true population parameter is. I have this distribution of sampling error, and I know what the shape of this distribution will look like, but I don't know what the midpoint is. I don't know what that true population parameter is. And then I'm going to ask this question: within how many standard errors will 95% of samples fall? Notably, I'm going to ask about 95% of the samples because I want to create a 95% confidence interval. So I ask this question: within how many standard errors will 95% of samples fall? And we just answered that question on the previous screen when we talked about a critical value. So if I calculate the degrees of freedom for my sample, if I know my sample size and determine degrees of freedom, then I can look up a critical value on a t-table, and say I go to my t-table and look up the critical value, and if I had a very large sample, that critical value, for example, would be 1.96. And that answers this question. That means that 95% of samples will fall plus or minus 1.96 standard errors of that true population parameter. So in this case, I'm saying I don't know what that true population parameter is, but here's this point right here. This is the point 1.96 standard errors above that true population parameter. And then here's the point below. I'm drawing my red line below here. Here's the point 1.96 standard errors below that true population parameter. And on the screen, I have this green double-headed arrow section here, and that's showing the section that spans from 1.96 standard errors below that true population parameter to 1.96 standard errors above that true population parameter. And I know if I have my sample size and look up my critical value on a t-table, if that critical value is 1.96, then I know that this is what it looks like, that 95% of my samples will fall plus or minus 1.96 standard errors, and 2.5% will go higher than 1.96 standard errors, and 2.5% will go lower than 1.96 standard errors. So altogether, 5% of the samples will be more extreme than 1.96 standard errors, and 95% of the samples will fall within plus or minus 1.96 standard errors of my true population parameter, if 1.96 is my critical value based on my degrees of freedom. Now, I'm going to use the term bandwidth to describe the distance above or below the true population parameter within which 95% of samples will fall. So for example, if I have a very large sample and I go look up my critical value on a t-table, and if the critical value is 1.96, that is the critical value for a p is less than 0.05, given my degrees of freedom, if that critical value is 1.96, then I know 95% of the time samples will fall plus or minus 1.96 standard errors for my true population parameter. And so 1.96, that's my bandwidth. 95% of the time, samples will fall plus or minus 1 bandwidth from that true population parameter. 95% of the time, they will fall plus or minus 1.96 standard errors from that true population parameter. So 1.96 is my bandwidth. So I mentioned that a critical value gives us a bandwidth, but it gives us a bandwidth in standard error units. It tells us within how many standard errors do 95% of the samples fall. It is giving us a bandwidth based on standardized units. But if I'm calculating a confidence interval, I don't want to use standardized units. I want to use the original scale for whatever statistic I'm working with. For example, if I calculate a mean difference, that is, I calculate the size of difference between two means, I want to know the bandwidth for my actual mean difference values and not something measured in standard error units. I want to be able to say something like, the true population mean difference is somewhere between a mean difference of this and a mean difference of that. I want to give my answer in terms of a range of mean difference values that I am 95% confident will capture the true population parameter. I want to give my answer in terms of a range of mean difference values and not a range of standard error values. If I say the true population parameter falls plus or minus 1.96 standard errors, that doesn't really tell me where I think the true parameter is. But if I say the true mean difference is somewhere between a difference of 2 and a difference of 5, well, that provides useful information. So, whereas my critical value is giving me a bandwidth in standardized units, I want to unstandardize it. I want to unstandardize that bandwidth so that it gives me a bandwidth using the original scale for whatever statistic I'm working with. Now, note that to calculate a t-value, when we calculate a t-value, we divide a statistic by its standard error, and that is what standardizes the scale. So, if dividing by a standard error will standardize our scale, then multiplying by a standard error will unstandardize it. So if I take that critical value and multiply it by a standard error, it will give me the bandwidth for that actual statistic using the original units of my statistic. So that's what we're going to do. To create a bandwidth for a statistic, we will first figure out the critical value based on the sample size, and then we'll multiply that critical value times the standard error for that statistic, and that will give us a bandwidth for that statistic. It will give us a bandwidth using the original scaling units for that statistic and not standard error units. So we know that if we replicate our study over and over, we know that 95% of samples will fall plus or minus that bandwidth. So let's summarize where we are at this point. So here is a distribution of sampling error for a mean difference. Now, notably, my picture is showing X bars, whereas these should be Y bars, but let's say this is a distribution of mean difference values. That is, I do a study and I calculate a difference between two means, and then I replicate my study over and over and over an infinite number of times. And so this would be the distribution of all the mean difference values I get when I replicate my study over and over and over again. And the midpoint of this distribution, the midpoint will be the true population parameter. However, I'm no longer assuming that the null hypothesis is true. I'm no longer assuming that that parameter is 0. In this situation, I simply do not know what the true population parameter is. However, if I look up a critical value for p is less than 0.05 based on my sample size, if I look up that critical value on a t-table, and if I multiply that critical value by my standard error for my statistic, I will get this bandwidth. In other words, if my statistic is a mean difference, I would simply multiply the critical value times the standard error of mean difference to get my bandwidth. And I know that whatever the true population parameter really is, I know that 95% of the time samples will fall plus or minus 1 bandwidth from that true population parameter. That is, if I replicate my study over and over and over, and each time I calculate a mean difference value, I know that 95% of these mean difference values will fall in this green area, that is, the area in between the two green arrows. 95% of the cases will fall within that green area. That is, 95% of the time, samples will fall plus or minus 1 bandwidth above or below the true population parameter. 95% of the time, the statistics for my samples will fall in this green area. Now, on the previous slide, we saw how the green area on the figure was calculated as the area falling plus or minus 1 bandwidth from the true population parameter. And we know that if we replicate our study over and over, 95% of the time, the statistic from our sample will fall in this green area. So for example, if my study involves calculating a mean difference, then I know that 95% of the time, the mean difference I get from a study will fall in the green area. So now consider this. What would happen if I do my study and I calculate a mean difference for my sample, and then I put the bandwidth around the mean difference for my study? In other words, I do a study and calculate a statistic, and I put the bandwidth around the statistic from my study. Note that if the statistic from my study falls in the green area, then the bandwidth will include the true population parameter. On the slide, I have some red dots towards the bottom here, and imagine that each red dot represents a statistic that I got from a single study. Say I do a study and calculate a mean difference, and say this top red dot, say that represents a mean difference I got from a single study that I conducted. And this study got a mean difference, you can see it's just a little bit higher than the true population parameter. The true population parameter is the brown line going up and down. And if I put that bandwidth around the statistic from that top study, note that this bandwidth includes the true population parameter. It goes over it. So if I do the study and get a mean difference that's a little bit higher than the true population parameter right here, put that bandwidth around that mean difference that I got from my study, that bandwidth includes the true population parameter. Or we look down a bit lower here, this middle dot, or towards this dot towards the left, that would be I do a study and calculate a mean difference, and this study gets a mean difference that's quite a bit lower than the true population parameter. But note that if I put the bandwidth around this mean difference score, if I calculate the statistic for this study and put the bandwidth around that statistic, note that that bandwidth still includes the true population parameter. That blue arrow still barely crosses that brown line right there at our true population parameter. or at the very bottom, I have a study where I calculate a statistic that's much higher than the true population parameter. I put the bandwidth around that statistic, and note that these blue bars, they still cross that true population parameter. That bandwidth still includes the population parameter. And every time I do a study, if it falls in the green area, if I put the bandwidth around the statistic for my study, that bandwidth will include the true population parameter. So we know this: 95% of sample statistics will fall in the green area. And when a sample statistic falls in that green area, the statistic plus or minus the bandwidth will include the true population parameter. So if I do a study and put the bandwidth around the statistic for my study, 95% of the time it will include the true population parameter. So I can say that I'm 95% confident that my statistic plus or minus the bandwidth will include the true population parameter, and that is the 95% confidence interval. That's how we do it. So, in summary, here are the steps for calculating a confidence interval. First, we need to use a t-table, and we need to look up a critical value for p is less than 0.05. And so based on our degrees of freedom, we look up a critical value for p is less than 0.05. And notably, we use p is less than 0.05 for a 95% confidence interval, and we would use a different p-value if we wanted a different confidence interval. So once we have our critical value, then we need to calculate the standard error of our statistic, and then after we've calculated the standard error, we simply multiply the critical value times the standard error, and that produces this bandwidth. And then we simply add and subtract that bandwidth from our statistic, and that produces the 95% confidence interval. And that is everything for Part D of Unit 3.